This lesson examines the simulation of a basic series voltage regulator using LTspice. The circuit combines a 12-volt Zener reference with an NPN transistor connected as an emitter follower. The unregulated input is 20 volts, while the regulated output is expected to be approximately the Zener voltage minus the base emitter voltage. That gives a first estimate of 11.3 volts. We will compare this hand estimate with the simulated operating point and then test whether the output remains stable when the input voltage or the load changes. These two tests are called line regulation and load regulation. Follow the circuit from left to right. The unregulated supply feeds the Zener node through the 220 ohm resistor. The Zener diode holds this node close to 12 volts. Transistor Q1 is connected as an emitter follower, so the emitter output is about 1 base emitter drop below the base voltage. The resistor current divides into Zener current and base current. The transistor then supplies a much larger emitter current to the load. This current gain is important. The load does not directly draw its full current from the Zener reference, so the reference voltage is less disturbed when the load changes. This is the netlist for the voltage regulator circuit shown, and this netlist was used for simulating the circuit behavior. The operating point analysis agrees closely with the hand calculation. LTspice gives a Zener node voltage of 12.092 volts and an output of 11.375 volts. The simulated base emitter voltage is 0.717 volts rather than the assumed 0.7 volts. The Zener current is approximately 35.7 milliamperes, while the load current is 11.375 milliamperes. The pass transistor dissipates about 97 milliwatts. These differences are expected because SPICE calculates the transistor junction voltage and Zener behavior from the device models and the actual currents instead of fixing them at ideal values. Line regulation tells us how much the output changes when the unregulated input changes, with the load held constant. Here, LTspice sweeps the input from 14 volts to 26 volts while the load remains 1 kilo ohm. Across this 12-volt input range, the output changes by only 51.3 millivolts. Dividing the output change by the input change gives a line regulation of approximately 4.3 millivolts per volt. This is only 0.45% of the output voltage. The plot therefore confirms that the Zener reference and series pass transistor reject most of the input supply variation. Load regulation tests the output while the input voltage is held at 20 volts and the load resistance is changed. The sweep covers 200 ohms to 10 kilo ohms. This corresponds to load current changing from approximately 56.7 milliamperes down to 1.14 milliamperes, a range of nearly 50 to 1. The output shifts by only 101.7 millivolts or 0.89%. At the heaviest load, the output dips slightly because transistor base current increases. That additional base current is drawn from the resistor Zener node, reducing Zener current and lowering the reference voltage slightly. The simulation validates the basic design. At the nominal operating point, the output is 11.375 volts. Line regulation is about 4.3 millivolts per volt and load regulation is 0.89% across a very wide load range. The pass transistor dissipates approximately 97 milliwatts, while the Zener current is about 35.7 milliamperes. These values must be checked against component ratings in a practical circuit. We should also verify the minimum Zener current at low input voltage, transistor power at high input and heavy load, and sufficient input to output headroom. Hand analysis gives insight. LTspice checks the assumptions and reveals non-ideal behavior.